Okay, I'm going to get started here in a second. Surprise. I know most of you don't know there's going to be a talk going on. So if anybody in the room is interested in analog malicious hardware, then there are plenty of seats up here. Come up here and make friends. Come learn something new potentially. Malicious hardware, and analog. So I should be taking a lot of people's low-level buttons. So come on, let's have a talk. It's better than waiting in line. Okay, so today I'm going to be talking about some actual research that we've done at the University of Michigan. My name is Matthew Hicks, and this research was on a team with Kai-Yun Yang, Ching Dong, Todd Austin, and Dennis Sylvester. And we're going to tell you how to actually take the power of analog circuits and analog behavior and use them as a very stealthy and small attack in digital hardware. So before we get started, some background, right? So foundations are important, right? You can see from the building here, whatever you build on a weak foundation, even if it's the strongest building in the world, is also weak. Every computing system, even our badges that we touch, at the foundation of that computing system is hardware, right? So even if you say I do cloud security, cyber, whatever, you have to trust and rely on hardware. And almost everybody here, people that aren't listening exactly, they implicitly trust hardware. But surprise, hardware itself has bugs. And in past work, I showed you how those bugs could represent security vulnerabilities themselves. And if you have somebody you don't trust that adds bugs to hardware, those bugs are very powerful because they infect the entire hardware stack. So even if you have the perfect crypto on top of this, OpenSSL is made robust against everything. If you have a vulnerability in your hardware, it represents a vulnerability in your software or network. And the added benefit or drawback of hardware is it's not very easy to patch. So you generally need to get FedEx on the phone and go to the hardware hacking village and take out the soldering iron, because that's how you generally patch hardware. It's not as easy as software. And so I know most people probably outside of here are security-centric. You've all done a great job in building fences. And I know we're going to explore how robust those fences are with the hackers in the crowd. But generally, software security community has done a great job building defenses. But attackers still are motivated. Maybe that gets out script kiddies, but a large set of attackers are still motivated to attack you. They're just not going to give up, right? They need to make money themselves. So what do? They try to go below your defenses. If your defenses are perfect, the only way to combat that is to try to rule out, to violate some of your assumptions. And software people make a lot of assumptions based upon nothing about the hardware. So we've already seen this in reality. If you can kind of squint your eyes, you can see it says rootkits. You then go down lower to malicious hypervisors, bootkits, and in last years we've seen this spread of malicious hardware. So kind of in the academic space, we've seen two types of attacks. And they're all based upon how am I going to prevent my attack from being noticed? Well, one of them says, hey, listen, I know you're going to run some sort of functional verification, some testing, and I don't want my attack to actually influence behavior, so I need to hide it. How do you hide your attack? Well, you use this thing called a trigger, which is basically just a very complex state machine to basically nest your attack in the dark recesses of the state space of the processor. So you have imagine a bunch of if statements in software, something like that makes the condition to trigger the attack very, very unlikely to be accidentally or even intentionally bumped into. So on the other hand, we see saying, well, yeah, there's some drawbacks to having this big complex trigger because it takes lots of hardware to implement it. That's a large perturbation of hardware. Well, what if my attack was always on? That'd be really small and it'd be stealthy against a certain set of defenses. So before, our work, which is called A2, you've seen this kind of yin and yang of hardware attacks, where you're either stealthy and small but always on, or you're stealthy against testing, but you have this large trigger to kind of hide you. So researchers noticed this and they said, hey, we're going to divide the space too, and we're going to try to conquer each thing separately. So the defenses you see here to visual inspection and side channel. So you see a lot of this stuff now. Maybe not visual inspection here because you really can't, pump photons or ions into chips here. We don't have that kind of circuitry. But you definitely have side channel analysis, and there's some talks that I'll be attending talking about side channel analysis. Well, what do those types of defenses work well against? If you have a large perturbation in hardware, then it's going to have a large dynamic signature, like it's going to change power when it switches. Or you can even what's called delayer the chip or fib the chip and actually see the malicious hardware. And you can only do that if you have this large perturbation, this large state machine that's trying to hide from the other defense, which is dynamic and static analysis or verification. So dynamic and static analysis, what they do is they say, if you are always on or if it's easy to trigger your attack, I want to find the test case in a practical amount of time that triggers that malicious behavior so I can identify it and say, for whatever reason, I don't trust this chip. And so you've kind of seen this dichotomy of just divide and conquer of the space. And really what we started asking when we started this project is this real? Is this assumption real? That you can really just divide the space and there is no in between? Or is there a space in the middle where you can implement an attack that is both stealthy from visual inspection and side channel analysis and doesn't require a lot of gates and hardware? So it's, because it doesn't require lots of gates and hardware and it actually encodes a very complex state machine so you won't accidentally bump into it or a defender won't be able to find it. And so kind of a pictograph of this challenge is here you can see a state machine. This just represents an abstraction of hardware complexity, the gates it would take to make a complex state machine. And over here, this is the ideal. This is a cell, which is kind of the primitive. When you build actual what's called ASICs, you do full custom VLSI, you're kind of playing around with transistors, and the basic building block that you deal with is something called a cell. So if we can have all this expressibility, this functionality, which hides from static and dynamic analysis, and express it down into something that's just as small as the most functional unit, basic primitive with which you build digital hardware, then we have created that something that's in that gray space that hides from visual inspection and side channel analysis and hides from dynamic and static analysis. And going even higher level, look at this as the game of Where's Waldo. So we have a kind of a die shot of a processor, and it's pretty easy to see Waldo, and Waldo's our attack. But if you can go down to the most primitive unit, when you fib a chip, it's going to become a game of Where's Waldo, where everything looks like Waldo. So everything, because your attack is expressed in the most basic unit of digital hardware, everything could be an attack circuit, and you have to not trust anything. So that's really the goal that we're trying to meet. All this functionality to hide our attack from dynamic and static analysis in the most primitive unit of hardware, a cell. So before I get into it, some of you may not know the kind of design process of hardware. It's kind of similar to software before fabrication. So you have your specification stage where you have some text of the specification in English language or whatever language. Then you implement this specification. HDL, which is a hardware description language, the same thing like a software description language. You take that and then you want to formally/functionally verify it. You can't formally verify everything because that's an intractable problem. And in fact, hardware complexity is drastically outpacing the complexity that formal verification tolerates. It's even getting worse. So the stuff you can't formally verify, you want to functionally verify. Automatic test pattern generation, you kind of want to run test cases through it. So once you get this done, you say, I have something which I'm confident is a correct implementation of my specification. So you pass it off, and now we go into the different stages. So this is all like software, and you can see you have a binary, which is similar to a netlist. But the problem is, a binary you can run on every computer. A netlist, you actually need to be able to hand somebody a physical chip. So that requires some more steps. So I hand somebody this netlist, and I say, hey, I don't have the skills to do this, or some of these steps. I need you to actually create hardware for me. So the first thing you do is you take that hardware netlist, which is all the basic blocks, you lay them out, you connect them together using metal, and you make sure everything passes timing. You create a GDS2 file, which we'll see in a second, which is basically a bunch of polygons which represent metal that are wires connected together. And you go to fabricators. So TSMC is a great example. Say, okay, I actually need you to build me this. let's say you have $100,000. Most of us can't afford to build our own, but in university we can. We hand them the GDS2 file and $100,000 and say, hey, build me 100 of these. And they do that, and they do their own testing to make sure they didn't make mistakes. Because unlike software, when you build hardware, there are variations that occur that make each hardware unique. And we'll come back to that later on. Then, when the foundry gets done, TSMC mails you back some chips, and you go through this kind of layers of, you do your own in-house testing to try to detect faults that TSMC missed. You do your own system integration, adding this hardware to other pieces of hardware. You can do that at the hardware hacking village. And you have this other supply chain, eventually leading to a FedEx truck and an end user getting a complete system. So this is kind of the high-level space, and we're going to focus on not the design stage, which is above the first dash line. We're going to focus on threats in this stage right here, which is the start of the supply chain or just fabrication time attacks. So let's see what you get. So you can either, this is what a netlist looks like. It's still just a text file. It's less human readable. But an important point is it does have meaningful names. If you go down a little lower, if you were actually to build it, place and route your design yourself, you could hand TSMC this kind of like art looking thing here, which is just a visual representation of polygons that represent wires connected together. This is called a GDS2 file, and this could be fabricated directly. And we're going to focus on this. All the attacks work in either space. We're going to focus on, well, what can this person at this stage do? And this is, without loss of generality, more complex because these are the same except for this has meaningful names, and this is literally polygons with X and Y and Z coordinates. So this is called a semantic gap. You have less information to attack the circuit than you do here. Like, where's my privilege bit? Where is this thing I want to attack? So here comes the kind of main point of the talk. So most people in here probably haven't built malicious hardware, although it's very likely that's done here than any other talks I've given so far. If you do, this is kind of what it looks like. So this block of code is pseudocode for what we call a counter-based trigger. And basically the attack works like, the longer I execute my processor, the more likely it is that the attack will be deployed. And so it's very simple to implement this with a counter that looks for this threshold value, 1, 2, 3, 4, 5. If I'm below this threshold value or not at it, I add 1 to my counter. And then whenever I hit this value, it says do the attack. And this kind of code is run every time this RBACE signal, this is a wire and hardware, every time this toggles. And RBACE stands for rare, meaning that if I run my benchmark or defense program on here, it doesn't trigger, it doesn't call this signal to toggle. So it doesn't activate this code a lot. But the attacker can load stealthy code on the system once it's deployed that artificially creates an increased toggle rate. So that's what rare but attacker controllable event means. And we'll call this our, because it's hard to say rare but attacker controllable all the time, we just call that our victim wire. So really we're going to want to implement something that replaces this, that gives you the effect of a counter-based trigger when you attach it to some victim wire. But this takes a lot of logic. You have at least 32 bits to hold a count. You have a mux to decide whether you need to add 1 or not, and then to unleash the attack. So because it has lots of logic, it makes it more susceptible to visual inspection or side channel analysis. So what we have is this very simple operation. Observation that a capacitor acts as a charge accumulator or as a counter of charge. So as you see here, the red represents charge on the capacitor. There's kind of an orange dashed line in the capacitor. That's the threshold. In the analog domain, the capacitor, its voltage increases as you increase the charge on the capacitor, just like a counter. But if you take this output of this, the voltage on this capacitor, and you try to read it as a digital values only have 0 and 1. They don't have 2.7 volts. So that orange line represents where the output of the capacitor gets interpreted as a 0, then to a 1 in the digital domain. So really, we operate in the analog domain, but eventually it has some digital circuit influence. So we need to convert that analog value to a digital value, and that orange line represents our threshold. So you can see here, these are almost analogous, except for the capacitor is actually more complex because capacitors, they leak. So if you have a capacitor, you charge it up, and you don't connect it to anything, eventually you'll come back to it, and it will have 0 volts on it. It will lose all of its charge. Well, that's kind of a leaky bucket counter, which has a great impact for us because that means you can get what they call spurious activations. So you put some charge on there accidentally, and it will forget about that the longer in time you go. So that's the high-level observation. Capacitor acts like an accumulator. So the rest of it is just how do we actually implement that to get the effect that we want. And so this is the effect that we want. Start at the top of the slide. This is a kind of a black box diagram. So we have that victim wire, remember, rare but attacker controllable event. And that's in the digital space. And that wire will toggle. And what we want to have is this black box trigger behavior, which you see here. And that works in the analog space. And then eventually it produces an output, which is analog, but will be interpreted as a digital value, which will basically deploy our attack or not. So this victim wire has some toggling here, and we'll go through the steps in a second. This is our capacitor voltage. And notice there's a red line, dash line here at the top, which is whenever the voltage on the capacitor goes above that line, that means our output of our trigger circuit is interpreted as a 1, do attack. If it's below that line, we'll see in a second, it's generally 0, don't attack. There is a harder to see green dash line right below it. And that's actually where if you are attacking, if you say do attack, you don't actually turn off until you get the voltage on the capacitor below this line. That's called hysteresis, but it's real functionality at a high levels. It gives you an attack window. So I, as an attacker, can run software which says, pump up the charge, accumulate charge in this capacitor. And then once I know it's above that level, I don't have to keep running that code anymore. I need to run other code to give you a permanent attack. So there you can read Linux's memory, read your process structure and make modifications, actually weaponizing the attack and giving it kind of higher software level meaning. And so this difference between the red line on top and the green line on the bottom is this hysteresis, which gives you that effect. And then on the output is the digital value of our trigger, which you'll see in a second. So there's kind of 3 important phases. So the first one is the attacker may actually kind of cause toggles or just maybe background toggles to your victim wire. And you want your attack trigger to be robust against that. So that's what we have here. There's a couple triggers. They don't happen a long time or there's space between them. And you can see charge gets accumulated on the capacitor but not enough to release the attack. But then after the toggling stops, because of capacitor leakage, it kind of forgets about this spurious activation. So it's like you got close, but you didn't get enough. So I'm going to kind of forget about it as time goes on. And you can see the output of our trigger is still a don't attack, a 0. So in the next phase, the attacker wants it. Now the attacker runs their code on there, which wants to actually accumulate enough charge on the capacitor to deploy the attack. So in this case, they run software which creates a high enough toggle rate and for a long enough period of time to actually accumulate more than enough charge on the capacitor so that the output eventually changes from a 0 to a 1. So now you will deploy the attack. And we'll get to what the attack is later on. And then, I don't know how many of you have heard about Heisenbugs in software, but this is like a hardware Heisenbug here. You don't want once you start your attack, you don't want your attack to be on in hardware all the time. You actually want it to kind of disappear because it makes it really hard to find because you don't know how you triggered the attack and you don't know, when it was triggered or for how long. So you want to kind of, release the attack eventually. And so we'll take advantage again of capacitor leakage and we'll get below that dashed green line and eventually our attack will disable. And this is called the retention time from when we go on to when we go off. And that's the time frame you have to modify software where you have high enough escalated privilege where you can actually take a hardware attack and make it a software level persistent attack. So the hardware attack is not persistent, but you have a retention time window to make your attack persistent from the hardware level to the software level. Now, this could be the last slide, but it's great for us. It's not because we never would have got a paper out of it. You're probably thinking, well, that's interesting, but just connecting a capacitor, some wire in the design doesn't seem that interesting, right? Well, let's analyze that theory. So I have a capacitor and I'll connect it. And let's start out when our victim wire is 0. Well, the current value is 0. We have no charge in the capacitor. Everything works in this case. The problem comes, so we change values. Our victim wire goes to high or to 1 value. And that basically starts accumulating charge very quickly on our capacitor. So quickly, in fact, that with almost instantaneously, within a clock cycle, your capacitor is at full charge. But our problem was we wanted this complex state machine, not an attack which was triggerable within a single clock cycle, within a single toggle of a wire. So we just can't add a simple small capacitor to the design. And now you're probably like, well, that's a small capacitor, I understand that. Small capacitors don't hold a lot of charge. But what if I had a really large capacitor? Well, one problem is we're implementing this in full custom ASIC, so you can't actually implement very large capacitors. We're talking femtofarads. Femtofarads, it's below nano, so it's very small. And even if you could implement a large capacitor actually affects the surrounding components much more, has large current spikes as you try to push current into that large capacitor to fill it up. So that makes it more obvious from a side channel analysis perspective. So you can't use a small capacitor, you can't directly connect a large capacitor. What can we do? Well, we thought about this and we said, well, what if we, instead of having one single capacitor, what if we had two capacitors? A small, what we call unit capacitor, and then a relatively larger, still femtofarads, larger capacitor. And then we do what's called charge sharing. I'll load up charge very quickly in a small capacitor, and then I'll throw a switch, and then I'll connect this capacitor to this capacitor. And when you do that, capacitors what's called share charge. They basically agree upon a common voltage. And so you see here, all this charge on here gets shared with the larger capacitor. And because, again, the unit capacitor is relatively small compared to the main capacitor, it takes several fills of the small capacitor to eventually fill up this much relatively larger capacitor. So that's the premise of how we get the effect that we're looking for. I'm going to kind of run through it here and a little lower. So each of these, we implement this all using transistors. A capacitor, they're so small because they're just wire lengths in a design. It's not actually, you're not actually adding a physical component capacitor, you're choosing the capacitance and wire lengths. And so what we have here is that two transistors. These gates are hooked up kind of complementary to one another. This gate closes when victim wire is 0. This gate closes when victim wire is 1. So they're kind of mutually exclusive. When this gate closes, it charges up this small unit capacitor. When this gate closes and this one opens, it disconnects this small capacitor from power and connects it to the other capacitor in this kind of charge sharing. And if you do this several times, toggling the victim wire, you will gradually charge it up. So let's see what that looks like. Okay, so we start out with 0, and you can see the victim wire goes from 1 to 0. On 0, remember, this unit capacitor is connected to power, and so you can see it almost instantaneously fills up the charge on the unit capacitor, bringing it to VDD. But again, the output of our attack is on the main capacitor. So the victim wire will toggle again, and as soon as it does, that connects the capacitors in charge sharing, and now basically both the capacitors agree on a much, much smaller common voltage. And so if you do this for long enough, you will eventually pump up the charge on the main capacitor high enough so that its output, its voltage in the analog domain, when interpreted in the digital domain, now is a 1, do attack. And so that's how we use charge sharing to give you that ideal behavior of accumulating charge in a stepwise fashion on a capacitor. So that's kind of like the high level attack. But that actually doesn't buy you much besides like, oh, that's an interesting thing. We actually want to demonstrate this in a real design. So what's the next step that we needed to do? Well, what's an appropriate victim wire? Remember, some of the properties we had are, it's rare. It has a low level common case toggling in the background or for whatever kind of testing suite that we're going to run on it. But the attacker can control it using kind of user mode code. So we need to find wires in the design that do that. There's details in our paper, which is freely available on my website, impedimenttoprogress.com, along with all my other stuff. You can read about it. We basically reverse engineered the design and used simulations to figure out wires that were in both sets. And some of our selections are, the most important one is divide by 0. That's the one everybody understands. So in the processor we do, there's a flag that gets set every time you do a division by 0. x86 is a little different. And we're going to attach that, that's going to be our victim wire. We also can use signed division with unsigned division. In the paper, we go into multi-stage attacks. So using this as a building block, this analog trigger is a building block, and how you can connect them in different ways to kind of trade off how large your attack is for, our trigger is, for how nestled in the space it is. So we're going to use division by 0. What does the code look like that triggers it? So this is my very simple academic code to do this. How I did this is I had some idea about how to use volatile to do it, and I compiled it, looked at the assembly, and said, that's not a dense enough toggle rate to trigger our attack. And so this is what I ended up on, which is kind of still highest enough level in C. You could also do it inline assembly if you want. But the things to notice here are, this is user mode code. If you want to look at all the code going into your system, you would look at this and say, oh, that looks fine. It's not using any special instructions, no privileged behavior. All it has is 2 fundamental components. The first one is division by 0. So the division by 0 takes that flag which says division by 0 and moves it from a 0 to a 1. If you follow it up by another division by 0, that flag would stay at 1. So that's why we have the +1 afterwards. That +1 is an arithmetic operation which resets the division by 0 flag. So with these 2 operations, divide by 0 plus 1, divide by 0 plus 1, the rest of the code is just getting that packed into enough in assembly so that we have the high enough toggle rate. But this is all we do, and this doesn't have any problems. Oh yeah, questions are awesome.
Why use C1 here? Why can't you just use C?
So you can't use C because the volatile means it'll have to read that register every time. So yeah, there's some. Don't worry about this too much. I played tricks with volatile, and the embedded people might know. But yeah, so I wanted an initial read of that C. I want to separate those A, B, and C off to be different registers. Because basically what I want to do, instead of writing inline assembly, I want to have the compiler not optimize my code away as having no effect. So I need the A, B, and C to look different, but actually be 0. So that's what volatile does there. I want to read it once. I don't want you to read C every time. So I use C1 as my intermediate, which is not volatile, so it can say, oh, the compiler says, oh, I know that value is going to be the same every time, because if you use C, yeah. So the initial was not that clever. It was in assembly, but this is kind of a high-level way to do it. Okay, so with that, I implement attack. We do some reverse engineering to actually find the wires, and we have some C language which will actually trigger the attack. Well, what's this attack? What do we actually do with this? Because so far I haven't told you what it does. The asterisk means our trigger is attack agnostic. We don't actually care what the attack is. In this case, we do something that most people can understand, which is called privilege escalation. So think if you're on x86 LAN, you run in ring 3, and I want to go to ring 0 or ring -1, which some of you may not even know exists. This is the attack that does it. What privilege you're executing on is stored in what's called a register. What we do is we simply take the digital interpretive version of our trigger output and reset that flip-flop or that state that holds it. Now, why does resetting the state work? Think about it. Every time you restart your computers, it starts in the most trusted mode and then gradually de-escalates privilege as you boot the system up. So we partially reset part of the hardware, and there's no software to de-escalate privilege, so we're naturally in the most privileged state of hardware. And that's why this can apply to any register you want or anything really in the system, because all systems start at the highest privilege and they de-escalate down. All systems that I know about do that. So that's our attack. And when you have that attack, what can you do with it? You can run any instruction that you want in the system. You can read arbitrary memory. And so what I would do is I would start reading the kernel's process structs, find my process struct, and escalate my privilege in the process struct by changing memory. And you have that retention time window to do that. So some of you from x86 land, this is going to be a little different. So from here I have we implement this on the OR1200, which is an open source RISC processor. Here's a snapshot of the instruction set specification of a page for it. And really the next question is, okay, I have my attack, I know what wire I'm attacking, I know how to trigger it. But how do I know when I can spend cycles on escalating my hardware attack to software instead of just trying to trigger my hardware attack? And this is called, checking for success. And so we use this special instruction. It's different for different architectures. The key points are, this is how we kind of read and modify privilege registers. Notice, you can only do this from when you're in supervisor mode, or let's say ring 0 in x86. But on the OR1200, if you do this from any other lower privilege level, what happens? Nothing happens. So this is kind of a context-sensitive behavior. Many processors have that. It's not just an open source thing. ARM has some of these. One thing to look for is something called read as 0. So processor designers say, hey, it's actually more efficient for us just to return a 0 value if you try to read something you shouldn't be reading, as opposed to giving you the actual value or giving you an exception. So what they do is they have this context-sensitive behavior. When you read a register, if you don't have privilege, it's 0. If you do have privilege, maybe because of our attack, you have some non-zero value. So we'll do our attack sled, and then we'll read this register. If we get anything other than 0, we go escalate our attack to the software level. And so that's what we do. Okay, there are a lot more challenges than I have time here today. There's a lot of low-level analog, because when you go at this level, lots of things leak when you kind of build a full custom ASIC. And there's kind of a thing we have to do there. How do you actually find this? We describe better the reverse engineering that we did. And then I talk about multi-stage attacks, kind of making this a general thing. So to recap, before we get to the evaluation, what we have here is we operate on 2 levels. The blue boxes here in the top and the outside, that's the digital domain. And we also operate in this orange block, which is what implements our capacitor, in the analog domain. All the defenses that exist today for malicious hardware that don't look for like side channels, they operate in the digital domain. And when you take this design and you pop it up, try to make a digital representation of it, this behavior disappears. So you can't actually you can't actually image a chip and rebuild the digital circuit because this disappears. Now, if you try to actually characterize the analog behavior, there's things called SPICE. But anybody in here who's ever done a SPICE simulation knows you can't do it for a full processor, number one, and if you can, you can't do it for hundreds of thousands of clock cycles that it takes. It's just too low level of information. So, that's how we get around all the defenses. So we had the attack, we told you about finding victims and how to activate it and check for success. Well, now how do we integrate that into an existing chip? So we get something that kind of looks like this, and we had to find a place to put it. You would think that would be hard, but unfortunately, it's a 2-second slide. It was actually easy because all commercial chips have probably about 30% free space, black space in design. So inserting one primitive unit, one cell, is trivial in this. You don't create it. Why do they have this for the people not to know? Because routing is a very hard problem. It gets exponentially harder the more utilization you have, the tighter your area is packed with devices. So they keep the utilization fairly low, below the elbow of the curve, to make it tractable for tools to automatically lay out your design. So that wasn't actually a problem for us. We actually built this, I forgot the actual prototype at my house, but because this exists in both analog and digital domain, it's not something we can run in an FPGA. Yeah, we ran simulations of it. We ran hardware simulations, but the hardware simulations can't do the analog behavior. We run analog SPICE simulations, but again, you can't simulate a whole processor, so that simulated the analog behavior of our trigger. To put them together, there's no tool that exists for that, so we had to actually build a chip. And so this is the OR1200 we built. You can see a couple of levels of zooming in to see basically our one cell attack in amongst many other cells, about 100,000 transistors worth. So we built it, and so real quickly, some experiments. So what you're seeing here, it's a histogram of wire toggle rates. So on the bottom you see how much does this circuit wire toggle in relation to the clock. And then on here you see the proportion of signals that toggle at that rate. And you'll see here, it's not kind of interesting because we were very pessimistic with how we implemented this, but this red highlighted bar is actually a bar. That's the bar that contains our division by 0 signal. And as you can see, we even went through all of our benchmarks. We picked the most division by 0 heavy kernel of our mathematics benchmark and just ran that alone. And that produced a toggle rate of 0.0002. So basically, essentially, is 0. This dashed line tells you that's our threshold. So you have to toggle for a certain amount of time above this dashed line. So move this red line above this dashed line for enough time to fill up the charge in the capacitor. If you're below that red line, so if this solid red line is below that dashed red line, you are not keeping pace with leakage. So you don't actually end up accumulating any charge. As you can see here, we were way too pessimistic with how we built our threshold and our circuit. But this is an animation, by the way, of running our one of our our most division heavy benchmark. And this just gives you an idea how close we are to spuriously activating our attack. The short answer is not close. Well, the next question is, we see here from the snapshot of that animation that your benchmarks, even the benchmark that gets the closest, doesn't even come close to your activating the attack. But can you activate it as an attacker? So this snapshot is running that division by 0 code that I showed earlier, user mode code, and the solid red line is right here. And these are all division by 0 and sign division related signals, and you can see it's well past that bar. So defenders can't trigger our attack without knowing exact specifics about it, but we can load user mode code that can trigger it ourselves. Okay, so last little bit, I kind of lied to you about some of this stuff. This bar, I actually picked a random number where that was in previous slides. It's actually a question, where does that bar exist in real life? And those of you coming into the hardware space, every processor has a bar in a different location due to the manufacturing time variances. So you get a little bit more metal here, a little metal here. The capacitors are actually different ratios relative to each other. So that moves that bar around. So as an attacker, I want to be able to kind of simulate where this bar is at. And why do I want to do that? Well, if the bar ends up being, if I thought it was over there and it ends up being back here, well, then a benchmark could trigger the attack. And then I would slip in my attack, and then every device would be obvious that this attack existed. And kind of on the other side of the spectrum, if the bar is pushed way out in toggle rate, then I can't even toggle at a fast enough rate to put deposit charge in that capacitor, and so I can never attack anything. So we want to make our attack, our trigger, not trivially triggerable, but a knowledgeable attacker can trigger it. But we don't want to have to build a chip, because again, most of us don't have $100,000 to build 100 chips that nobody will use. So we want to rely on simulation. If simulation is fairly accurate, then an attacker can simulate their circuit at different nodes in the space, and then they can have high trust that it will end up that way. So what you see here on the rightmost column is our simulated value. Typical corners are just the operating environment and manufacturing variances. So we can see 7 for the first example. And then our measure, we take 10 chips out of our 100, and we measure where that bar is at and take an average. And our average is 7.4. And so what this kind of high-level results tell you is the attacker doesn't have to build the attack circuit to have confidence that where they think that bar is going to be at, where they think the threshold is going to be at, it's going to really be at that threshold. In our case, our threshold was, none of our circuits were trivially activatable, none of them we couldn't activate, but we were still way too pessimistic given that our benchmarks barely toggle our wire. Good question. So yeah, variance, you're assuming the distribution is normal. I think it actually is normal. I would actually have to look for what the variance is. No, yeah, I think it is a normal. I think those they're natural processes, and I think it is normal. Is a standard different? Yeah, but that's a good question. I don't know why. I don't even know if we have that in the paper, the variance of, but I was thinking the same. But again, that's why I say none of the chips we couldn't activate, and none of them we could, although the margin, least slack that we had was actually between the toggle rate that we could toggle it at and where that threshold was. So if we're going to err, it'd probably be that we couldn't actually activate our attack on some chips. But that's a great question of what the variance was, because it is important to know. I don't think it wasn't for certain devices, and by the way, it's device dependent. Certain devices have more. So okay, there's a lot more there are more experiments in the paper. You can talk about it afterwards. Okay, so that's kind of the end of my pitch. You can always ask questions afterwards. The whole point of this is, we're the first to show that you can't just divide the attack space trivially anymore, that these kind of cross-layer attacks that are both incredibly small and working on no perturbation attacks are incredibly small and still stealthy. They can hide from static and dynamic analysis. Our attack is controllable, it's stealthy, and currently you can only detect it. There's no known way to detect it. The only signature you have is side channels. And so from an academic sense, we need to probably move forward and assume that there's some bit of malice in our hardware, and we need to make hardware that's robust against that malice. We can't just assume that somebody's going to invent a malicious hardware panacea detection tool that's going to work. That's what researchers have been doing. I'm guilty of doing one of the first papers of that. Although I was on the first paper that said that doesn't work, so I got to double dip there. But we really need to, when we build systems as hardware, if any hardware engineers, you really need to think, what happens if I can't trust this? Or how do I make it so my system can still work, provide value without trusting this thing here? And I'm looking into those areas as well. So high level bit, I believe in being as open as possible. There are some things we cannot share with this, like the cells, because that's proprietary. So there's some information about fabbing the chip. I have go to my GitHub repo. Lots of my other paper stuff's on there if you backtick a couple times. And my website for finding this paper, other hardware security and other papers, impediment-to-progress.com. With that, I can answer questions. We can take questions offline if you want. I don't really know the format, but we have 15 minutes. Any public questions? Public questions? Yes, sir. So as an attack, is the question, as an attacker, could I do more complex, stitch more together, more complex behavior instead of just looking for one simple event? I look for multiple things. Yeah. So we go towards that by showing you how to do a couple of these things together in a multiple stage attack. Recently, I've been thinking about doing a paper where I can show you how to map existing digital attacks into analog only attacks. So there is no fundamental limitation. Anything you can think in a digital space, anything that's been thought of in a digital space, I can actually tell you how to implement that using our analog techniques. The trade-off, though, is the more you do, the larger your attack is, so it might be easier to spot using visual inspection, or side channel analysis still wouldn't be that great for what we're talking about. But yeah, we're looking towards that. That's the next thing. Yes, sir.
So you mentioned moving more away from detection to thinking about the...
I think we need to couple detection with making it, assuming that we're going to have some malice. Detection is still valuable for certain.
Yeah. For this particular attack, it seems like, are you thinking of in terms of trust, what processor you're bringing in, or what would you...
Yeah, I think of, so my high level pitch is hardware right now is what we call monolithic. So operating systems, you have microkernels, you have monolithic kernels. Hardware is just monolithic hardware. So even if you build things in modules, you put it together and you fab it, it's all one big monolith. And I think we need to start thinking about breaking hardware itself into layers. And then at the bottom of this, you will have a trusted layer, and then you can build on top of that. So, it's always a trusted computing base going to the bottom. Well, you don't just stop at hardware, you need to go deeper into hardware and break that apart into layers itself is what I think you need to. And that, and in terms of how you design it and even how you fabricate it, there are coming technologies in split manufacturing, 2.5D, 3D integration technologies. And I think those can all be combined. And then when you divide and you say, I only need to trust 1/100th of my design, that makes it more amenable to formal and functional verification. And you can actually spend more time on that. But I think you really should say, here's stuff I don't care about, I don't need security, and here's stuff I do need security in. Let me focus my efforts on the stuff I do need security. Right now it's just one big gobbledygook. Yeah. So, yes, ma'am. What's that? We're using what? So actually that's, I've been trying to. So one observation, and I think what you're hinting towards is, and I learned about this actually after we even published the paper, most manufacturers put spare cells on the hardware itself. I don't know if you knew about that, but that's what you're, so right now I could actually say we have a zero modification attack because we don't have to add a cell. Most manufacturers actually put spare cells. And that's when you see processor steppings. What they're doing is they're taking spare cells and recoding logic in those spare cells because it saves you the NRE cost of having to do an entire remask and respin. It's very easy to connect things up after the fact, cheap to connect things up after the fact. So they actually put spare cells to basically populate the entire thing when they ship it because they know, we can just do a very low level patch. Yes, we could take one of those spare cells and flip it out with our own and we would have probably even a more stealthy attack. So does that answer your question? Yeah, we thought about it, but I didn't learn about it until afterwards. So, yes, sir. I think in the future you'll see things that question is more suitable towards. Not this, but there's a wink in there somewhere. I think there's the zero modification attack. I think that's where that's one area I'm interested in going towards, where you get plausible deniability. Anyone else? Okay. If you have any private questions, come and see me afterwards. Otherwise, thank you all for attending. I know this was mysterious. I didn't know where it was at either. Thank you.